Hello, everyone. I'm Juan. Today, let's talk about a fascinating class of material, piezoelectric materials, and why symmetry is the key to their function. Have you ever used a gas lighter that clicks and sparks when you press it, or a quartz watch that keeps perfect time? These devices rely on the piezoelectric effect, the ability of certain materials to convert mechanical force into electric charge. But not all the crystals can do this. So the big question is, what makes some crystals piezoelectric and others not? That's what we will uncover today. Let's start with a simple definition. The piezoelectric effect is when a material generates an electrical charge in response to mechanical stress. But not all the materials can do this. Only certain crystals with very specific internal arrangements show this property. So what kind of structure do we need? To answer that, we need to talk about briefly two things. One is crystal structure, how items are arranged in 3 dimensions. The other is symmetry, how the structure looks under rotation, reflection, or inversion. A central symmetric crystal has a center of symmetry. If you invert every atom through a certain, the structure looks identical. In such a crystal, any charge generated by compression cancels out due to the symmetry. No net polarization, no piezoelectricity. In contrast, non-central symmetric crystal lack this internal balance. When stressed, the asymmetric charge center shift, generating a voltage across the material. So, asymmetry is the origin of the piezoelectricity. This is why materials like quartz, barium titanate, or zinc oxide nanowires are piezoelectric, but sodium chloride or diamond are not. Now that we understand the structure-property relationship, let's briefly talk about how piezoelectric behavior is quantified. There are 3 parameters. There are 3 key parameters. D33. This is the piezoelectric coefficient. It tells us how much electric displacement we get per unit of mechanical stress. Think of it as the sensitivity of the materials. G33. This is the voltage coefficient. It describes how much electric field is generated per unit of applied stress. Very important for sensors. Coupling factor K. It represents conversion efficiency between mechanical and electrical energy. Think of a piezoelectric material like a springy net full of small weights, dipoles. When you press on one side, the whole net shifts, creating an imbalance, and out comes electricity. But if the net is perfectly symmetrical, pressing it does nothing. The magic lies in their tiny asymmetry. This structure-functional connection is a beautiful example of how atom scale geometry leads to a real-world function. Let's quickly review what we have covered. Piezoelectricity is the coupling between mechanical stress and electric charge. Only non-central symmetric crystals show piezoelectricity. Materials like quartz or barrier titanate are functional because of their structure asymmetry. Key performance indicators like D33, G33, and coupling factor allow us to measure and optimize piezo materials for sensors, energy harvesters, and actuators. In material science, structure determines function, and asymmetry creates opportunity. Thank you. In the next session, we will look at how we can design new piezoelectric materials from organic building blocks like curves, and how crystal engineering lets us control symmetry and at the molecular level. Thank you very much.